Alright, so in this video, this is going to be the second order linear homogeneous differential equations. Case 3, I have to break this into a couple parts, so this is part 1. So of course we have ay double prime plus by prime plus cy equals 0, which is star. That's our generic homogeneous differential equation, second order. Characteristic equation is ar squared plus br plus c equals 0, and the quadratic formula gives us that r equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And case 3, this is where b squared minus 4ac is bigger than 0. And what does that mean? That means we have two complex roots. And so we'll just say that r is going to be alpha plus or minus beta I. Okay, so I've got a couple little theoretical things to do, but here's going to be what the claim is. The claim is going to be that the homogeneous solution is going to be C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. Okay, so that's going to be what the claim for the homogeneous solution is. There's several things I need to do before we can even get to where we believe that. Interestingly enough, so all throughout, like, you know, we've had this phrase, there's no I in calculus, so every time you get an I for an answer, like if you're trying to find maxes and mins and you get an I, you throw it out. So this is actually, you know, and just think about any word problem you've ever been solving. You get two I's an answer, that's meaningless. That's not going to be the price of a candy bar or whatever. So this is the first time where you have an I in an answer to something and it actually means something. So this is significant. You know, you've studied that in pre-calculus and you've never ever used it, and now we have a chance to use it. So from now on, you should note that if you have I's in things, it means there's going to be sines and cosines. It means you're going to have some kind of periodic circular behavior. All right. So I've got several things to prove. So first thing, I'm going to prove an abstract theorem. I'm going to write it down, and then I'll read it. Okay, so here's what the theorem says. So if z of t equals, let me make sure that's clearly a z, if z of t equals u of t plus I times v of t. So this is a complex function that has a real part and an imaginary part. Okay, so if that's a complex solution to star, which is ay prime plus by, ay double prime plus by prime plus cy equals 0, then u of t and v of t are both real valued solutions to star. So that's how we're going to get these two things, okay? All right, so here's the proof. So we're going to let z of t equal u of t plus I v of t. And we need to, so if we're going to sort of talk about it being a solution, we need to take two derivatives. Now, you may be wondering to yourself, what do I do with the I? Well, it's just a constant, right? It's just a number. So you treat it as a constant. So this would be u prime of t plus iv prime of t, and z double prime of t is u double prime of t plus iv double prime of t. Okay, so when I substitute this in, I'm going to not put the of t's because it's just going to be more, they're just going to get in the way. So we're going to substitute that then into star. So that means we're looking at a z double prime plus bz prime plus cz. Okay, now keep in mind here, the theorem says that this is already a solution. So a lot of times when we're trying to show something as a solution, we want to get an answer of 0 in the end. In this case, we can already assume that it's equal to 0 because we've said it's a solution. Okay? So then we substitute what these things are equal to. So this is a u double prime plus I v double prime plus b u prime plus I v prime plus c u plus I v. And once again, we know that's already equal to 0. That's 0, not 6. Okay, and then what do we do to sort of get what we want? Well, it's a real common thing that we see in these types of exercises and proofs. We regroup. So I'm going to put all the u's together, and I'm going to put all the v's together. Now notice that all the v's have an I with them. So I'm going to factor that I out. So this is going to be a u double prime plus b u prime plus cu, and then I a v double prime plus bv prime plus cv, and that whole thing is equal to 0. Now, we're talking about this is more or less a complex number. This would represent the real part, that would represent the imaginary part. So when, let me just sort of put it up here, when is a plus bi equal to 0, well, that means both parts have to be equal to 0, right? So a equals 0 and b equals 0. So applying that to this situation down here, I've got a real part plus I imaginary part equal to 0. So both of those two parts have to be equal to 0. Okay, so this implies that a u double prime plus b u prime plus cu equals 0, and a v double prime plus bv prime plus cv equals 0. Okay, and those are both real valued functions, so there we go. We have the proof. So I'll say that's the end of it. Okay, so how do we sort of get to the general solution that I claimed? So we use something called Euler's formula. And maybe you proved this in your BC classes, maybe you haven't. I know I usually do it. So this is a way that ties in all those transcendental functions together. So e to the I theta is equal to cosine theta plus I sine theta. This is real easy to prove if you use the Maclaurin series for all three of these and just substitute things in. Just pops out right away. So it's like a 3-line proof. So I won't go through that, but we're just going to use that formula. Now we've already proven that if R1, and look, R1 was abstract. We didn't say R1 had to be real. If R1 was a solution to the characteristic equation, then e to the R1t is a solution to the differential equation. So that means e to the, and I'm just going to take one of them here. I'm not going to use the minus sign. I'll come back to that. E to the alpha plus beta I t, that's a solution. Okay? And like I say, we already proved that. We proved that abstractly in a way that didn't matter whether it was real or complex, whether the characteristic root. So let me just go through and derive something then. So we've got that e to the alpha t, and you know when you have e to the a plus b, that's e to the a times e to the b. Kind of like we did in first order differential equations when you had, the right hand side was kt plus c and you exponentiated both sides. So this is e to the at times e to the, let me write it this way, I beta t. Okay? And then if we use Euler's formula for the e to the I beta t, we get that this is equal to e to the alpha t times cosine beta t plus I sine beta t. And then let me just spill all that out. So that's e to the alpha t cosine beta t plus I e to the alpha t sine beta t. Okay, and if you're wondering why we did this after we did the other one, so let's go back up to the theorem here. The theorem said if z is u plus iv, then u and v are both real valued solutions. So coming back to this, that is like the u of t, and that is like the v of t, and that's why, let me come back to the top, my claim says that YH is going to be this, where that's my u and that's my v, and I do have to show you one more thing, which I'll show you in part 2, that these guys are linearly independent, and that'll be kind of messy, but this is going to be your general solution.